Hi everyone. In this lecture we post on the first lecture of this unit. If you remember, we talked about the problem of the Königsberg bridges. This was a city called Königsberg in which they had a river with two islands and several bridges, seven bridges in total, connected as it is seen in this picture here. Okay, and the problem was whether it was possible to follow all the bridges one by one and without repeating any of the bridges. Okay, you could start in a place and end in a different one, or start in a place and end in the same place, but you had to follow all the bridges just once, and all the bridges must be followed. Okay, so this was a problem that the famous mathematician Euler considered and solved, creating in the process what is today known as graph theory, or all the concepts that we have been studying in this unit. Okay, and you remember that we said that we can state this problem as a problem in a graph. Okay, so here we have a graph in which we have all the elements that we need to consider in order to solve the problem. We have the four different regions, the two banks of the river, the two islands, and the connections among them. The bridges in this case are the edges, and the different places, the banks and the islands are the vertices of the graph. Okay, and the idea is that we want to find, if possible, a path that uses all the edges in the graph once and only once. We can generalize this idea to other graphs, like for instance this uh, toy car here, or this toy model of a house, and consider that where two or more edges or lines join, we have a vertex in the graph. Okay, and the idea is again whether we can form a path that uses all the edges once and only once. Okay, and in this case, this is another type of game that you may know of, which consists of trying to draw a figure without lifting the pencil of the paper, and without retracing any of the lines. Okay, so you can use a line, an edge in the graph once and only once. So this is exactly the same kind of problem that Euler considered in order to solve the Königsberg problem, and now we are in a position in which we can answer this kind of question with our knowledge of graph theory. Okay, so let me define this in a more formal way, and we say that we have an Eulerian path in a graph if this path uses every edge once and only once. Okay, and if the path is a cycle, then it is known as an Eulerian circuit, okay, or cycle. And we say that the graph is Eulerian if it contains one of these paths. Okay, so our goal in this lecture is to try to find a way of determining if a given graph has a path that uses all the edges once and only once, and if we determine that there is such a path, then to find it. Okay, so that is what we are going to do, and we are going to solve completely this kind of problem for any kind of graph. Okay, so this is a you will see a very powerful result, but it's also very easy to understand and very easy to check. This is a property that might seem complicated to check, but you will see that it's very, very easy. And in fact, it has to do with a notion that we already know about, which is the notion of the degrees of the vertices. Remember that we have defined what are the degrees in a graph. In this case, we are considering non-directed graphs. So the degree is the number of edges that are incident in a given vertex, and we have also studied in different cases what is the number of edges in the number of degrees in a type of graph, like for instance the complete graph or the cubic graph or something like that. Okay, so this is important because it is completely closely related to the problem of finding paths which use all the edges in the graph once and only once. Okay, so what we need to define is what we call even and odd vertices. So a vertex is even if it has an even degree, and it is odd if the degree of the vertex is odd. Okay, and the number of odd vertices in a graph is going to be the key property in order to check whether there is an Eulerian path uh, in the graph or not. Okay, for that we need first a couple of results, a couple of theorems that are very easy to prove, but that will give us a clue in order to check later whether we have these types of cycles, these types of paths in a given graph. Okay, so the first theorem is that when we have a non-directed graph, the sum of all the degrees of the vertices in the graph is an even number. Okay, and this is very easy to see. Let me first give you an example and then we prove the result, but it's very, very easy. So let me draw a graph, any graph that you want, something like this, for instance. Okay, and let's count the degrees of the vertices in this graph and then sum all of them. So this vertex has degree 1, this has degree 2, this has degree 3, again this one has degree 3, 3, 2, and for the central one we have 1, 2, 3, 4, 5, 6. Okay, so now we have to add all these numbers here. So we have 1 plus 2 plus 3 plus 3 plus 3 plus 2 plus 6. Okay, so we have 3, 6, 9, 12, 14, 20. Okay, 20 is the sum of all the degrees in this graph. Okay, of the vertices in this graph. And as we have stated in the theorem, of course, this is an even number. Why did we know in advance, without summing up all the numbers, all the degrees of the vertices in the graph, that it was going to turn out to be an even number? Well, the idea is that when we sum up all the degrees of all the vertices in the graph, we are counting each edge in the graph twice. So for instance, this graph here contributes both to this degree and to this degree. Okay, so each edge is counted twice, once in one of the extremes of the edge and another time in the other degree. Okay, so when we sum up all the different degrees in the graph, we have twice the number of edges, and since it is twice a number, it is always even. So that is the simple proof of this result. Okay, so this is the first theorem that we need. The second theorem that we need is that the number of vertices with odd degree, that is the number of odd vertices in a graph, is always even. Okay, so this takes a little more time to prove, but it's also very easy. But first, let's check that this is the case in this graph. So what are the odd vertices here? What vertices have odd degree? So we have this one with degree 1, this one with degree 3, this one with degree 3, this one with degree 3. Okay, so we have 4 um, vertices with odd degree, and 4 of course is an even number. Okay, so again in this graph the result is true, but it is true in general. How did we know that the number of vertices was with odd degree was going to be even? Okay, so the idea is again the same. If we sum all the degrees, we know that this is an even number. Okay, that is exactly what we have stated in the first theorem. But we can decompose this sum into two sums. So the odd degrees on one hand and the even degrees on the other hand. Okay, so we can decompose the sum of all the degrees into those degrees that are odd and those degrees that are even. In the previous case, for instance, we have that the odd degrees are 3 plus 3 plus 3 plus 1, while the even degrees are 2, 2, and 6. Okay, so this would be one part of the sum, and this would be the other part of the sum. Okay, but we know that this number is even, the sum of all the degrees. Of course, if we sum even numbers, we obtain an even number. So this number here is also even. So we are summing something with an even number and obtaining an even number. Okay, in this case we are summing this number here, which is even, and we are obtaining 20, which is even. Okay, but if this number is even and this number is even, this number has also to be even. Okay, because if it were odd, odd plus even would give us an odd number, but we know that the result is always even. So this again must be an even number. Okay, but in order to obtain an even number when we add up odd numbers, because remember that in this part here we are summing up only odd degrees. Okay, so we are summing up odd numbers. So if we sum up odd numbers and we obtain an even number, the only possibility is that the total number of degrees that we are adding is even. So here an odd number plus an odd number makes an even number. Another odd number plus another odd number makes again an even number. Okay, so the number of odd degrees must be even, because in that case what we obtain when we add up all the odd degrees in the graph is going to be an even number as required. Okay, so with this we conclude that the number of odd degrees in a given graph must be even. So we can have, as in this case, for instance, 4 odd vertices, we can have 2 odd vertices, we can have 6 odd vertices, we can have 124 odd vertices, but we cannot have an odd number of vertices. We always have an even number of vertices. We cannot have a graph with, for instance, 7 odd vertices. Okay, that is impossible. Of course, we can have a graph without any even without any odd vertex. For instance, this one here. In this case, all the degrees are 2. We have no odd vertices, but this is consistent with the theorem because we have 0 odd vertices and 0 is an even number. Okay, so in general we always have an odd number of vertices. Okay, and with that, with those results, now we can give a general result in order to solve the problem of finding Eulerian paths on non-directed graphs. Okay, and this is what we have in these two theorems which completely solve the problem. Okay, so we are going to consider a graph in which the number of edges, the set of edges is non-empty, because if it is empty, then of course the result is trivial. We have a path without edges, which of course consists of all the edges in the graph, once and only once. So we are interested in cases in which there is at least one edge in the graph. Okay, and what we have here is a result that is surprisingly simple. It is very simple to deduce whether a graph has a cycle or a path which is Eulerian or not, um, because we only need to take into account the degrees of the vertices. Okay, so in the first case, we know that we have a circuit that uses all the edges of the graph once and only once, if and only if every vertex has even degree. Okay, and also we need something else. We need that all the vertices are connected somehow. Okay, so we could have, I will explain in a minute, we could have vertices that are disconnected as long as they don't have any edge. Okay, so as long as they don't have their degree is 0. Okay, but all the vertices without with a non-zero degree must be connected, must be in a single connected component. Okay, another way of saying this result, which is what we will use in practice most of the times, is that if we have a connected graph, okay, if we have a connected graph, then we have a cycle that uses all the edges once and only once, if and only if all the vertices in the graph have even degree. Okay, so that's what we need to check. Okay, so this is the first result. I'm going to give you an idea of the proof in a minute, and I'm going to give you an algorithm to find this cycle afterwards. But first, let me give you a result that follows directly from this theorem. So this theorem is for the case in which we have an Eulerian circuit, okay, a cycle which starts and begins in the starts and ends in the same vertex and uses all the edges of the graph once and only once. But we can also have Eulerian paths, okay, uh, paths that are not closed, that start and end in different vertices, but use all the edges in the graph once and only once. So again, in this case, we need that all the vertices which have non-zero degree are in a single component, in a single connected component. Okay, um, that is a condition that we need in order to be able to join those vertices together with a path. And then what we want to check is if the number of um, odd vertices in this graph is at most 2. Okay, and we will see that this follows directly from the previous theorem. So if we have no vertices of odd degree, then we have a circuit that uses all the edges in the graph once and only once. If we have at most 2 vertices with odd degree, then we have an Eulerian path, a path that uses all the edges in the graph once and only once, and this path may not be closed, may not be a cycle. Okay? And remember that since the number of vertices with odd degree in a graph is always even, then we can only have 2 cases in which we have an Eulerian graph, a graph with an Eulerian path, okay, or cycle. That is when we have no degrees of zero of odd degree, or 2 vertices of odd degree. Okay, because we cannot have just one vertex of odd degree. Okay, the number of vertices of odd degree must be even. So if we have 0 or if we have 2, which are the minimal cases uh, of degrees which are odd, then we have an Eulerian graph. Okay, that is what we get from this result. So before proving this and uh, using an algorithm to find these paths in the case that they exist, let's go back to the original question um, of the Königsberg bridges problem. Okay, so here we have this graph, and let's compute the degrees of the vertices. Okay, so here we have D with degree 3, A again with degree 3, B with degree 3. Okay, so now we have at least 3 vertices with odd degree. Okay, so this graph cannot have a path that follows all the bridges, all the edges once and only once. From the results that we have just stated, it is impossible to find a path of such property. Okay, and we also know that the vertex that we have in the middle, C, also has to have odd degree. Okay, because we have 3 odd vertices, so the 4th vertex in the graph also has to have odd degree. In this case, it is, of course, 5. Okay, so this solves the question. This is why the people in Königsberg were not able to find a walk using the bridges once and only once. It is impossible. Okay, and this was found by Euler, and he also solved the problem not only for this case, but for all the possible cases with any number of bridges, any number of islands, any number of banks. Okay, because the theorem that we have stated solves this problem for all the cases. Okay, let me check also these other graphs here and see what's the degrees in the graphs in the vertices. So here we have 3. This one also has 3. This has 2. This has 2, and this has 2. So it is possible to draw this picture without lifting the pencil, without retracing over any of the lines in the drawing, because we know that when we have exactly two uh, vertices with odd degree, then it is possible to find not a cycle but a path, not closed path, that uses all the edges once and only once. Okay, so this is a situation in which we can do this we can draw that um, graph without lifting the pencil from the paper. Okay, and without going through a line more than once. Let's see about the car. Here we have 3, 3, 3, 3. So again, this is a case in which it's not possible. If you try to draw this figure without lifting the pencil or without going twice over a line, it won't be possible. Okay, so you see that it's very, very simple to know when you can find this type of cycle or this type of path. You only need to count the the edges that are incident in each of the vertices. Okay, and again, this is a solution that works for any kind of graph. Also, it's a solution that is very easy to compute. If you have the adjacency matrix of the graph, remember that from that you can get the degrees of all the vertices in the graph just by summing up all the ones in the columns or in the rows. So you can answer this problem very easily. Okay, so let's go back to the theorem and see why this works. Okay, so to see that it is necessary to have no no vertices of odd degree in a graph in order to have a circuit, an Eulerian circuit, um, notice that the idea is that in order to have a cycle that uses all the edges in the graph once and only once, whenever you go to a vertex, you have to be able to get out from that vertex. Okay, let me do a quick drawing here. So imagine that you have a vertex and you go to another one. Now, in order to close the cycle, you need another edge to go out. Okay, and from this one, you need another one to go out. And once that you are here, you know another one, you need another one to go out. And from here, you need another one to go out. And maybe at that time you um, close the cycle. Okay, but whenever you go to a new vertex, you need another edge that you have not used in order to go out. So every time that you enter, you need another edge to go out. So that's exactly the condition of having an even number of edges in each of the vertices. So one of the edges is to go in, another one is to go out. If you use another one, different one to go in, you need a different one to go out. Okay, so that's why you need an even number of edges in each of the vertices of the graph. Okay, and it will turn out that this is also a sufficient condition. If you have a graph with this property, then you can find a cycle uh, which uses all the edges in the graph once and only once. Okay, and that is what we are going to prove with an algorithm. We are going to study an algorithm in the next slide that gives us this way of computing the cycle if it exists. Okay, but from this it also follows that if we have exactly two vertices of odd degree, then we have a path that uses all the edges in the graph exactly once, and it is a non-closed path, it is not a cycle, and ends and starts and ends exactly in the vertices of odd length, okay? Of odd degree. So imagine, for instance, that you have here this vertex, here this vertex. Notice that this one has degree 2. This one here, oh, let me do, uh, let me have it like this. Okay, but this is better. So 2 here, 2 here, 2 here, 1 here, and then 5 here. Okay? So the idea now is that, well, here we have 2 vertices of odd degree. But imagine that we use an imaginary edge connecting these 2 vertices of odd degree. Okay? Then instead of having here degree 5, we have degree 6. And instead of having here degree 1, we have degree 2. And now all the vertices in the graph have even degree. Okay? And we are in the conditions of the previous theorem. We know that there is an Eulerian cycle here in this graph. Okay? But this cycle is going to be using this edge here, which is non-existent. This is an imaginary, a fake edge. Okay? So what we do is we find the cycle using the fake edge, and then we break the cycle by eliminating the fake edge. And then, of course, we have not a cycle anymore. We have an open path that starts and ends exactly in the vertices of degree, because that's where we have broken the cycle, but uses all the real edges in the graph once and only once. So that's why the second result, the corollary here, follows from the theorem, because we can add a fake cycle, a fake edge, compute the cycle, and then eliminate the edge to create an open path. Okay, so that's the idea that we can use in order to prove this result. Okay, so again, it's very easy to check whether given graph has an Eulerian circuit or path. You only have to count the number of odd vertices, the number of vertices with odd degree, and if it is 0, you have the Eulerian circuit. If it is 2, you have the Eulerian path, a non-closed path that starts and ends in exactly in the degrees of odd, in the vertices of odd degree. And if you have more than that, if you have 4 or 6 or more odd vertices, then you cannot find a path that uses either closed or not, that uses all the edges in the graph once and only once. So how do we compute this cycle if it exists? Well, what we do is to use a recursive algorithm. Okay, I'm going to give you an example in a minute, and we are going to devote a whole lecture in order to compute this kind of circuits and paths in graphs. Okay, but I will give you an example in a minute. First, let me explain the algorithm. So this is a recursive algorithm in which we can choose any starting vertex. Okay, it doesn't matter. You choose the vertex that you want. You will maybe obtain a different cycle, but independently of what is the vertex that you choose, you are going to be able to find the cycle. okay? At least one, okay? Then you start from that vertex and then you go out of that vertex with an edge, and from the new vertex you choose another edge, and from the new vertex you choose another edge until you return to the vertex that you started with. Okay, and this is always going to happen. Why? Because we are in a graph in which there are no odd vertices. So what we know is that the degree of all the vertices is even. Okay, so when we enter one of the vertices, we have another edge to go out. Okay, so always we can always go out. Okay, but since we can always go out and the first vertex has also even degree and we have used only one of its edges, we must eventually return to that vertex. Okay, because we have a finite number of edges, and eventually we are going to find the edge that gets us back to the starting vertex. Okay, and this is all because the the degrees of the vertices is always even. So whenever we can enter, we can go out. Okay. So we do that until we return to the initial vertex. Okay? In this situation, we can have two different possibilities. Maybe we have used all the edges in the graph, and then we are done. Then we have found the cycle that we were looking for. Okay? If that is the case, we do not have to compute any other thing because we already have the answer. Okay? If we have not used all the vertices, all the edges in the graph, then we remove all those edges from the graph. Okay? And in this case, maybe the graph now becomes not connected. Okay? We will see an example later. Maybe in this situation, the graph is no longer connected. Okay? But any of the connected components is now a graph, which is of course connected because it is a connected component, and in which all the vertices have an even degree. Why is it so? Because we have removed edges that form a cycle, so we have removed an even number of edges from each of the vertices. Okay, because we have removed one edge to go in, one edge to go out. So we always remove edges in pairs. Okay, so we started with an even degree in all the vertices, and when we remove uh, edges in pairs, we still have an even number of edges. Okay, so we can apply the algorithm to all the connected components in turn. Okay, separatedly, we apply the algorithm to each of the connected components, and we obtain the cycle. And after we do that, we can connect that cycle to the third cycle that we computed at the beginning, okay, to form a big cycle. Okay, so we repeat the process with each of the connected components, and then we join the circuits with the original one. Okay, this is better seen with an example, but the idea is very simple. We choose a vertex, we generate a cycle. If it is not a complete Eulerian cycle of the graph, we remove those edges and then we proceed with the connected components, and we go back and use the algorithm in the other edges. In the other, and we use the algorithm in the connected components, and then we join the cycles with the original cycle. Okay, so let me do it this. Let me do this first with a very simple example, and then with a more complicated one. Okay, so uh, let's draw, for instance, a graph like this one here. Notice that in this case we are considering graphs that are not necessarily simple. Okay, for instance, here we have two edges connecting the same pair of vertices. Okay, but this is also what we had in the original conic spheres bridges problem. Okay, we had several bridges connecting the same bank with an island, so this is the general setting that we need to consider. Okay, so let's first check that the graph indeed has vertices which are all of even degree. So here we have 2, 2, 4, 4, 2, and the remaining one, of course, is 2, but we already know that it is even because since we have not found any odd vertex, we cannot have only one, so the remaining one must also be even. Okay. In any case, we have these vertices which are all even, and we know that we can find an Eulerian cycle here. Okay. So how to do this? Well, in this case, it's very easy. I can do something like this, for instance. Okay. Of course, I can do something like that. And I find the cycle that I'm looking for. But let's say that I do not see that possibility, and I do something very stupid. Okay, so for instance, I start at this vertex, I use this edge, and then when I get to this vertex, I use this edge again. So in this case, I have use these two vertices, these two edges, and I have returned to the initial vertex. So I'm in the situation in step number 2 of the algorithm that we have studied. Okay, so in this case, what I'm going to do is to remember that I have used this edge first and this edge second, and I'm going to remove these edges from the graph. Okay, that is what the algorithm is saying. So I'm doing it very in a very stupid way. Okay, I'm not choosing the best way to do it, but I want you to show you that even in that case, we can do it without having to think. Okay, if we apply the algorithm, we are going to find a cycle, even if we do not make the best decision at each step. Okay, so now we have two connected components. We have this connected component here and this connected component here. And of course, we can apply the result to these components. Now this vertex has no 4 degree anymore. It has degree 2. This one has degree 2 also. But it's again an even degree, okay, as we had stated before. This is an even degree. So we know that we can apply the result to these two cases, to this connected component and this connected component. And of course here, if I choose one of the starting of the vertices to start, this one for instance, the only cycle that I can select is the one that uses all the edges here. Okay, so I get here, for instance, this order of the edges. And the same in this other part. If I start here, for instance, I can go here first, then this one, then this one. Okay? So now I want to connect all the cycles. I have cycles in the original vertex that I selected, and then there are cycles in the two connected components that I obtain after removing the first cycle. Okay, so in order to connect those cycles, I need to see that this vertex is the same as this one. They are the same vertex. And this vertex is the same as this one. They are the same vertices. Okay? So what I can do, let me see if I can draw it here, is when I reach this vertex the first time, I can try to follow the uh, the the cycle that I have here. Okay, but I'm arriving at this cycle at the middle. Okay, because I started with 1, then 2, then 3. Okay, so I follow this. Now this is the second um, edge in this cycle, in the complete cycle. Now I use this one, 3, and then this is going to be 4, and I return to the same vertex. So I can now use this cycle here. I can go here. This is going to be 5, and now I get to this vertex that is the same as this vertex here. Okay, and now from here I do the same. I go to this one, I use this one, and I use the final one. Okay, so let me remove the intermediate steps. So this is the final solution with all the edges in the cycle. Okay, that's the idea. Let me do it for a case in which we have not all the vertices with even degree, but we have two vertices of odd degree. Okay, so this is incorrect. This should be a connected graph with two odd vertices. Okay, be careful with this. So we have a connected graph with two odd vertices. Okay, so now we have an algorithm to find the Eulerian path or Eulerian trail in this graph. Okay, what we do is what I told you in the proof of the theorem. We add a fake edge, and then all the vertices have even degree. We construct the circuit as we did in the previous case when we find an Eulerian cycle, and then we remove the fake edge. Okay, so that's the algorithm. Very simple. Let me do it with the case of the graph for the house that we saw in the first slide of this part, okay, of this lecture. So here we have that this vertex has degree 2, this one has degree 3, this also has degree 3, and these two have degree 2. Okay, so in order to solve this case, I need to add a fake edge between the two vertices of odd degree, and now the degree of these vertices becomes even. It is increased in 1 unit and becomes even. So now I can try to find the cycle here. Okay, let me remove the numbers with the degrees, because then it is easier for me to select the edges. Okay, and now in order to do this, notice that I can select any of the, let me give names to the, that is going to be useful. Let's give names to the different um, vertices, and then we select, for instance, vertex number 1, and we go in this direction. We are going to select a cycle. Okay, so we can do something like this, then we go in this direction, then in this direction, and then in this direction. Okay, so now in this case we have been uh, more clever than in the previous situation. We have selected at the very beginning one cycle that uses all the edges. Okay, because in this case I want you to show you, I want to show you what happens when we remove the fake edge. I'm not interested anymore in the problem with the connected components, because we have already seen how to deal with that. So now I can select the cycle uh, completely from the first step. Okay, we will solve more exercises like this one in a future lecture. Okay, so now we have this cycle here. We start in 1, we go to 2, then to 3, then to 4, then to 5, and here we use, I'm going to write like this in order to say that this is the fake edge that we are using. Now 5, then 1. Okay, so with this we are we have the cycle with the fake edge that we have included. Okay, and now we have to remove this edge in order to get the 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 actual path. Okay, we cannot use this fake edge. But then this disconnects. It seems to disconnect this cycle here, or this path here. But remember that this is uh, the same vertex. We start and end in the same vertex. So what we can do is to start from 5 and read the path in to the left, or to start in 2 and read the path to the right. It's the same. We are going to obtain a path with all the vertices with all the edges in the graph once and only once. So it's not important, and we have these two possibilities. So for instance, if I start in 2, I go to 5, then to 1, and notice that this one is this one here. So then I go to 2, then I go to 3, then I go to 4, and finally to 5. And this is the path that I find. If I read the path from 5 to the left, then I have the same, but starting from 5 going to 2. Okay, so let me draw the the graph with this path to check that in fact we use all the edges once and only once. So we start in 2. Let me first write the names of the different vertices, and so we start with 2, we go to 5, then to 1, then to 2, then to 3, then to 4, and then to 5. And without lifting the pencil, I have been able to trace all the edges in the graph once and only once. Okay, so that is the way in which we can solve this problem, even if there is not a cycle in the graph, but an open Eulerian path that uses all the edges once and only once. Okay? So as always, if you have any question, please let me know, and use the discussion forum if you have any question about this topic. Thank you for your attention.